Greaves, we're back. Let's talk about still simple harmonic motion, things wiggling back and forth. And let's see how we can graphically represent this stuff. So remember, right, I don't know, like a simple harmonic motion and energy, right? Well, what's really happening? Well, remember, energy is always conserved, right? So since energy is conserved, what happens? If I have something wiggling back and forth, I'm going to go from, say, U, spring, right? That energy is, whatever that value is, it's always that value, right? 10 joules, whatever. So we're going to wiggle back and forth from, say, spring potential energy to kinetic energy. Then that kinetic energy is going to get converted back to spring potential energy, kinetic energy, and then so forth and so forth, dot, 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 back and forth, right? So if that's the case, and remember energy is conserved, let's just call this E total, right? That's going to be equal to U spring plus kinetic. That could be some point that's like midway between my maximum spring compression and my equilibrium position where it's going to be fastest, and I can represent as what? 1/2 kx squared plus 1/2 mv squared. So this is how I would find maybe the total energy of the system, right? So let's take a look at a box, right? So here's, I should say a mass, right? Here's my spring, right? And let's say that it's going to wiggle, right? Or I should say go back and forth, right? So here's my equilibrium position. Here would be an amplitude to the right, right? Here would be an amplitude to the left, right? And let's see what happens to energy as this mass on the spring is going to wiggle back and forth, or I guess technically go in simple harmonic motion. So let's take a look at how my graph would look like here. So let's call this energy, right? And let's call this position, right? And let's say that right here is going to be my equilibrium position, right? Let's say over here is going to be my plus amplitude. And let's say over here, I don't know, I'm not making it, it's okay. Let's say minus amplitude here, right? So let's take a look at this box, right? And what's going to happen? All right, so let's take a look at the box where it's at this position right over here. Well, what does it have when it's all the way to the left? I'm going to use different colors here, right? So what type of energy is in the box when it's all the way to the left? Well, since the spring is compressed, I'm going to say it's have its maximum what? Spring potential energy. So that would be somewhere up here, okay? Now let's take a look. As the box starts to make its way back to my equilibrium position, that potential energy is going to get converted to kinetic energy. But how does that look? Well, let's take a look at potential energy. Potential energy is 1/2 kx squared. So my position is a square root function, right? Squared function, exponential, that's really what I meant, right? So over here, what happens as my spring starts to go push back to the equilibrium position, what does my graph look like? Well, since it's exponential, right, it's going to look something that looks like that, right? Where all that energy is going to get converted to kinetic. And then what's going to happen is it's going to start to do what now? It's going to start to go to my plus A position, right? And what's going to happen to my energy? It's going to get converted back. So this part is the potential energy get converted to kinetic. Now all that kinetic is going to get what? Converted to potential. So this, right, this red, right? So red would be how my graph would look for potential spring. All right, let's go to blue. Let's take a look at what my kinetic energy looks like as this box wiggles back and forth. Well, let's start over here. As the box is all the way over here and it's at rest, it's in its maximum, right, potential energy position, what am I going to look like? Well, there's going to be my kinetic energy. Well, how does kinetic energy behave? 1/2 mv squared. Lo and behold, kinetic energy is also dependent upon something that's raised to an exponent. So what is that graph going to look like? Well, what's going to happen to my speed, or velocity, I should say, as I start to make my way back to my equilibrium position? So if you guessed this, you are correct, right? right? So as it's making its way back to the equilibrium position, it's picking up speed because the potential energy is being converted to kinetic energy. And at this equilibrium position here, I am at my maximum kinetic energy or maximum velocity. And then what's going to happen as it passes through, right, that kinetic energy is going to be converted to potential energy. And if you do this, right, that looks good right there. Okay, so now what about my total energy? Well, remember, right, well, let's do this, right? So my blue line, that's going to be my kinetic energy. And, well, remember, energy has to be conserved. So up here somewhere, right, I'm going to have, right, my total energy. So this is, let's call it E total, right? And this guy will be E total, right? So that's going to be, in general, right, my graph for spring and kinetic energy and total energy for any object that's actually undergoing simple harmonic motion. Okay, so let's go through another couple of graphs just to look at some stuff. Yesterday I sent you guys that hand-drawn thing on the graph paper. If you haven't already, right, I would like you to stop the video real quick, go print that and bring that back, right, so you have that with you, right? So I'm going to bring this over now, right, assuming that you did that and restarted the video. So let's take a look at position, velocity, acceleration. We're going to turn over force, U of a spring, kinetic energy, and total energy for any object that's undergoing simple harmonic motion, right? So here we go. So I took, actually, in this particular case, I don't know, I could have done the same thing before, but I made a mass on a spring that's just wiggling up and down, right? Position 0, right, times 0. Here is my equilibrium position, right? I've pulled it down a little bit here and let it go, and obviously, as you can see, the spring is going to go in simple harmonic motion over a certain amount of time. So let's take a look. Well, what about position? Well, let's see, how does my graph of position look like? Well, all right, so time 0, I have time 0 all the way over here. What does my graph look like? All right, over here, notice I have my equilibrium position plus amplitude A minus amplitude A here. All right, so let's take a look at position for this object as it wiggles back and forth. So my position of the ball up here, right, is going to be somewhere on my positive amplitude, right? So let's make a little dot right there. There it is, right? And let's just say that this ball is already undergoing simple harmonic motion, right? So where's the ball when it's down here? All right, well, it looks like it is, in fact, at my what? Equilibrium position, right? Here's my equilibrium position here. And it is at the equilibrium position. Well, what about when it passes through the equilibrium position? Well, we're going to be down here. And what's going to happen now? It's going to make its way back up to what? The equilibrium position. Remember, this guy is kind of wiggling up and down over time. So there's this guy here, and then we're going to be over here. So how does this guy look here, right? How does this look? All right, so, right, we have something that looks hopefully like this. Okay, so here's going to be my graph of position versus time for an object that's undergoing simple harmonic motion. All right, well, let's see about velocity then. All right, well, what do we know about velocity when it's at these positions? Well, let's take a look. What do I know? Hopefully by now we recognize that the velocity is a maximum when I am what? At my equilibrium position, and it's actually stopped when it's at one amplitude away. So let's take a look. What is my velocity over here? All right, hopefully I get a velocity that looks like that. Okay, now I guess we have to be a little bit careful right here about how I'm drawing this next graph, because this guy is making its way back to my equilibrium position, but it's up on the positive, and believe it or not, it's in a negative velocity, right? It's making its way back to the equilibrium position. So at this point, it's a maximum, so it looks like I'm going to be down here. What's going to happen next? It's going to make its way, right, back, down, right? And it's going to be slowing down, right? It's going to maximum, slowing down, making its way back to my equilibrium position, or I should say, making its way to its farthest way away, which means that its velocity has to be what value? 0, okay? Then what happens, right? Believe it or not, here, it's actually traveling in which direction? It's traveling upward, so it's got a positive velocity, right? So it's going to be right there. And then what happens right there, it gets to its farthest away at its amplitude, and it's going to be right there. So this graph is going to be something that looks like this. Okay. All right, well, what about my acceleration? All right, well, where is the acceleration the greatest? Well, the acceleration is going to be the greatest, right, when it's farthest away. Remember, right here at the equilibrium position, right, what happens is, at this point, let's just say it's still traveling downward, right? As it's traveling downward, it's pulling the spring. And the spring force is going to increase as it gets farther away. So it seems to me that the acceleration must be greatest at what? At the amplitudes, because that's what we call the restoring force, right? So let's see, at this point, where is the acceleration? Well, the acceleration is going to be a maximum, and is it a negative acceleration or is it a positive acceleration? Well, it's going to be here, and which way is it pointing? It's going to be pointing to my equilibrium position. So it looks like I have something down here like that. Okay? Now what happens to my acceleration when I'm at my equilibrium position? Well, there isn't any, right? That's where it really wants to be, right? So it is, the spring up here is pushing it back down. It's at the equilibrium position. Oh, this is where I really want to be. But all of a sudden, when it gets through there, the spring is going to pull it back up. So at my equilibrium position, there's going to be no acceleration. What about, so that's here. What about here? Okay, the spring has elongated as much as it's going to go all the way to the amplitude, but it looks like the force on the spring is pulling it back up. So that's going to be my positive acceleration, right? Continue to go, negative, sorry, 0, and then down here. So in this particular case, hopefully you get a nice graph that looks like this. So there's my acceleration graph for this object that's wiggling back and forth. All right, so if you could turn the page, I have another sheet right here, right? We're going to turn the page and we're just going to look at three more things. What about force now? Well, hopefully, right, my force should match my acceleration. All right, so when my spring is up here, which way is the force, right? Which way is it pointed, right? It's actually a negative force because it's pushing which way? Towards the negative, right? So we got to start here. It's going to make its way to my equilibrium position, right? And it's going to look something that looks like that. Okay? All right, let's go back to my U spring and UK, which, by the way, I think we just went over last time. And what is the potential energy and kinetic energy graphs going to look like here? Well, up here I have a maximum, right? At this part, it's maximum, right? It looks like I'm going to get something that looks like this, right? And do that part very well, but it looks like that. So up here, when the spring is compressed, I have a maximum kinetic energy, right? It kind of behaves 1/2 kx squared, and it's going to be an exponential curve till I get down to my equilibrium position and zip off like that. How about kinetic energy? Well, kinetic energy up here has come to a rest. So it looks like we might have something, or not might, we should have something that looks like that. And then my total energy, well, obviously we know my total energy doesn't change, and it looks like something like that. So here are your graphs for some object that's in simple harmonic motion. What I'm going to do is I'm going to look through the textbook. I know there's some problems with this stuff, and I'll send that your way later today. All right, guys, see you later.